So to implement our hash table, we're going to need, as one of the operations, we're going to need our hash function to be able to map our key to a particular hash position. So let's have a look at how that works. So at a high level, like I just said, we're going to use our hash function is a way to map a set of keys, k, to a set of hash values. So we get our key as input to our hash function, and that's going to give a particular hash value. So let's describe some of the hash function's properties. The basic properties is that the key is type dependent. So that means it's dependent on the type of the item's key, whether that's a string, it's an integer, or whatever it may be. It has a return value in the given range, so it must fall within our array or our hash table, otherwise we can't actually insert it. So in this case it must be between 0 and the table size -1. Some of the desirable features include we want to make sure it's nice and fast, because if we have a slower hash function it may mean that all our operations can't meet the O1 promise that we're trying to meet. So we want to make sure all our arithmetic operations are limited, and if we have them they're going to be fast. We also want to minimize collisions. So basically a collision is when two keys map to the same hash value. We want to try and ensure that we distribute our keys as uniformly as possible. That way we can try and make sure that we, as much as possible, don't have any collisions. In a special case, the theoretical or the ideal would be that every key maps to a unique position. This is known as perfect hashing. Whilst this is good in theory for specialized prepared sets of keys, it's nearly impossible to achieve in real practice. So we'll see that later on, where it's a good theoretical aim, but we'll find that we just try and create a universal hash that means that as much as possible we avoid collisions or minimize the chance of collisions. So let's continue to look at hash function properties. Perfect hash functions are rare. It relies on very particular properties of keys and almost impossible to get in practice, like we just mentioned. Universal hashing is also nice in theory. It applies a family of hash functions. Basically there are k hash functions in that particular family of hash functions. Given a key, it picks a hash function from that family at random and guarantees the chance of collision is k divided by the table size, or less than or equal to that. Again, it's hard to achieve in practice, so it's sort of what we're aiming for, but it's hard to guarantee that. Good functions aim at getting closer to universal hashing. They emulate a random function's behavior and reduce the chance of collision through distributing the keys by hashes uniformly. So the idea is that we're trying to spread them out as much as possible to give good coverage over the hash table, but also try and reduce the chance of a collision. So how do we go about defining hash functions? Well, if we want to do it, if the key is an integer and we want to randomly distribute, position equals key mod table size. It would seem it's random and pretty fast. However, generating the key may not be a trivial task. For example, if we consider the key with these different inputs, for example, 033 could be a supplier number, currently up to 70. We could have a category code, such as 100, 150, 200, 250, up to 850, month of the introduction, year of the introduction, and also a checksum, some of the other fields modulo the 100, so that we just get it within from 0 to 99. So first observation is we've got data in there that's not really relevant, or it takes a long time to calculate. So for example, we could modify the key until all bits count, and the checksum should not be considered, and category codes should be changed from 0 to 15, because we've got a lot of wasted data that we don't need. So the point is we want to make sure our key is quick to work out and generate. That way we can apply the modulus and then get our final position relatively quickly. Let's consider another hash function. This time the key are basically words with up to 10 letters. One possibility would be to convert each character from a number from 0 to 25 and then add the first two characters to obtain the hash value. For example, if we had Maria, M is the 13th letter, or 12, and A is the first letter, or 0. So basically, if we add them together, that would give us a hash value of 12. Bernd would have B and E, which would be 1 and 4 respectively. So we add them together and we get 5. Melina would be 12 plus 0. So we can see we're not taking a lot of the data, so we're going to cause a lot of collisions. Basically, if the two characters are the same, and could be the same in any order, for example, MA would be the same as AM, we would get the same hash value, which is not very uniform. Second observation is the more elements, characters, digits in the key you use, the better hash function in terms of collisions. So if we had have used more letters in the key, we would have lowered the chance of a collision. Considering though that it has a cost as well, if we use all characters in the key, obviously it's going to make our hash function slower. Let's look at another way to implement the same hash function where we've got words up to 10 letters. Another possibility again would be to use the character from 0 to 25, add all of them together to get the hash value. So this time Maria would be 37, Bernd would be 38, Melina would be 40. So the smallest hash value is 0 and the largest is 250. So in this case we get definitely a bigger range of values because we're using more data in our key. However, we've still got a limited number of possibilities. We've got 250 different possible hash values. So if we wanted to insert 50,000 words, on average, we're going to have 200 possible collisions at each position. So which words? Anagrams would be an example of this because the positions are the same. Like I said on the example before, if you rearrange the letters, it would still return the same hash value because we're just adding them up. We're not actually taking the position into consideration. Third observation, using all elements is not enough to guarantee a good spread of possible hashes. We need something that uses all elements but also takes into account the position in the key. Have we seen this before? Think about the relationship between binary strings and decimal numbers. If we look at decimal numbers, for example, we've got 9, we know that's made up of 8 plus 1, if you're considering the binary. So each position has a different positional value. The rightmost is 2 to the power 0, next one is 2 power 1, 2 power 2, 2 power 3. So if they were all the same, it would just be 1 plus 1, but in this example, we've got 9 is made up of 8 plus 1. So we can see also 8 is just the fourth position, 2 to the 3, which we just use that value. 6 takes 2 of them added together to get us to 6. And same with 5. We can see that it's 4 plus 1. So again, the point here is decimal numbers can be seen as keys for binary words, that is, words made of 2 characters, 1 and 0. So let's apply what we've just learnt. So this time, again, we're going to use the key with up to 10 characters. We're going to, again, use 26, but this time we're going to use it to the power of its positional value. So for example, if we convert each character into a number from 0 to 25, otherwise base 26, multiply it by its position, its character position, and add them together to obtain an array position, or our final hash value. So we can see in this example, again, H is its hash position. We've got the character code, which is the same as before, but this time we're going to multiply it by its character position. So, for example, remember the leftmost is going to be its basically most significant position, so that would be n, and then n minus 1 as we reduce down. So again, if we apply this to Maria, we've got 12, 0, 17, 8, and 0, which were the basically character positions. 26 is going to be our base, and then we multiply it by its character position. We get the final hash value as over 5 million. And if we use our largest string, so if we had all z's and we work that out, it would be greater than 26 to the power 9, which is greater than 5 trillion, which is greater than 2 to the power 32. So it's good in the fact it's unique, hash value per word, but might exceed the capacity of a hash table. For example, a lot of architectures only allow a 32-bit index, so for example, or our array may be constrained to 32 bits, therefore it may go past the bounds of what we can actually store. So it's too big for our 50,000 words. There's a lot of empty hashes positioned in the array. So whilst it's very good, it's a little bit too much. It's too broad, the range of hash values that it's giving. Fourth observation, we want something in the range of our table size. Possible solution, if the number is too big, just multiply the table size. If it's too small, convert it to 0, 1, and then multiply it by the table size. But be careful, we might overflow or underflow. We're fortunate in Python, we don't have this problem because of arbitrary precision. It's able to resize and create numeric data types dynamically, whereas other languages might have a fixed size for numeric types. In our example, base 26 could overflow in Java. So possible solution is mod or multiply at each step. So if we remember, our hash function is defined this way. All we're going to do is basically take out the x at each step. Basically it's the same as saying ax squared plus bx. We just simplify by taking the x out to simplify it at each step. So then we do the multiplication by x each time we're going along, and then make sure that we just mod by the table size like we said before, so it doesn't become too large. And this is based on Horner's idea. So let's look at Horner's method a bit more in detail. So recall, we're defining the hash function as equal to this, and we're going to mod at each step, thus casting out multiples of the table size, making sure our number doesn't become too big. So let's use a table size that's quite small to begin with, just to illustrate this example. So if we define our hash function given a particular word, which is our key, the initial hash value will be equal to 0, and for each character in the word we're going to multiply it by 31 and then add it to our ORD, which is our ASCII value, and then mod by the table size. Now note here we use 31. We'll see why we use 31 rather than our 26 that we used before. And ORD A, like I said, is the ASCII value of that particular character. And we've got our table size. After we've done all that, we're then going to return our final value. Notice here we're returning as an integer, which is going to be the position in the hash table. So let's apply this to a particular example. So we've got this given key, A, H, and O. In this example, we're going to start with capital A. So we're going to firstly multiply 0 by 31, add the 65, mod by the table size, we get 65. Our next letter is 104. So again, we multiply by our base, which is 31, add the 104, mod by the table size, get 99. Finally, we feed that in, multiply it by our base, add the 111, which is the ASCII value for O, mod by the table size, we get our final value as 49. So if we were to apply the method where we just multiplied without modding as we went along, we could see our final value would be 65,800, and that's only on an example with 3 characters in it. So you can see that if we mod that by 101, we still get the same value. But the point here is that our value as we're going along never becomes larger than our table size 101, which just makes sure the key never becomes too large. So we said earlier, if the position is equal to key mod table size, generally it's random and pretty fast. If the key is not random, we use a prime table size. So it basically comes from pre-computed values. So if we were to, for example, not use a prime, then the table size may have common factors. So let's consider keys that finish in 0, they're all hashed to 0, and even if they don't finish in 0, if they're a multiple of 5, then they can have the same value as if you mod it by 2. So for example, if we have this table, you can see that there's a couple of examples like 5 times 3, 5 times 5, they all still go to the same hash position 5. So it's only discriminates basically between odd and even. It doesn't really give you anything other than that. So it's important that we just avoid common factors so that we don't have this issue. So that's why we use primes to avoid this, and that's why we chose 101 as the table size rather than some other number that has common factors. If you are multiplying by another constant, it's best that it's relatively prime or coprime, that it has no common factors. The same reason why we chose 31 earlier as the base rather than using 26. So you can see on this example, when we have a bad hash base and a bad table size, we've got one where we've got a collision occurring where two keys are both going to 104, but other than that you can see that they have very similar values. So one of the requirements was we want uniform, well spread out data. In this case you can see we're basically creating like a cluster of values around the similar sort of positions. We want to make sure that the data, like I said, is spread out as much as possible. So let's break this down to see how this works a bit more. So again, we're going to use our key from before. We're going to use the a base of 1024, and you can see our values 65, 104 and 111 being fed in. You can see we get the final value of 111. So since 1024 is 8 times 128, anything multiplied by 1024 is cast out when we mod it by 128. It means only the last character is kept at each mod step. So just be careful with that. We obviously, if we've got a base and a table size that has common factors, then we start to run into this issue that we lose a lot of the randomness or distribution when we don't use primes. So in this example between these two keys, you can see they have the same last character, so that means they hash the same position. Using a better hash function, we can see that the hash base is a lot better, 31 and 101, so they're both prime and coprime, so that means that we are going to result in no common factors, and you can see we have nice and sparse data. Nothing is close together, and in this case we don't have any collisions. Let's use another example. So in this example, again, we've got both primes on both the hash base and table size, but because we don't have a very large table size, we're starting to result into collisions. Alrighty, so how do we define a hash function? To summarize all this, even more effective than selecting a single coefficient like 31 is that you choose coefficients in a pseudo-random fashion. Use a different coefficient for each key position. So let's look at our example again. So like before, we're going to have A, which is going to be our initial base or initial coefficient that we're going to multiply each value by, but rather than keeping A the same each time, we're now going to multiply by a different prime, B, so that it updates its value. It's important that we mod it by the table size. We still want it to be within our range of our values, and we subtract 1 there because we don't want to end up with 0 or some weird value of A. We want to make sure that it does indeed change, so it's non-zero and also within our range. So with the final example here, we can see we've got values for A and B, our coefficients. They should be prime, just to make sure that we don't run into problems, and also make sure that there's no extra divisors. So that's, like I explained before, we want to make sure we -1 to ensure that we don't get an answer of 0 for our coefficient. We want it always to be greater than 0. So that's our final hash function. So obviously it's important that, like we've denoted in our hash function, we want it to be quick, but we also want to create sparse data, and the best way to do that is ensure all coefficients are prime, and also the fact that our table size is also prime. So in summary, our hash function is type dependent, must be within the array's range, should minimize collisions, each position is equally likely, and don't use non-data, so we're making sure that we're keeping it quick by using related data. Use all elements on or a reasonable subset if it's too large, and use the position of each element so we don't have issues with order and that such. We want to make sure that each position is considered again to take that extra information. Avoid common factors when modding, so whether that's the table size, for example, or the coefficients themselves. Like we said, it should be fast, so we should not have too many arithmetic operations, and it still be linear in the length of the element of the key. So basically you want your time complexity to be based on the length or size of the key. And of course it must be a function. So, and always return the same value given the same input. So if we give a hash function a certain hash key or the same hash key, it should return the same hash value. So same input data should produce the same output.